Today, let's talk about higher order derivatives and their applications in physics. Higher order derivatives are useful in finding things like velocity, acceleration, jerk, and beyond. And honestly, you won't ever really use anything beyond acceleration, but it's good to keep these higher derivatives in mind because who knows, right? So let's start with a simple example. And if you need to refresh your basic derivative skills, check out my video on derivatives. So let's say we have a particle. Its position is represented by the equation f of x is equal to 2x, where x is in seconds, and we're using meters as our unit of distance. So we know at 1 second, the position is going to be f of 1 is equal to 2 times 1, which gives us 2 meters. At 2 seconds, we'll have f of 2. That's going to give us 2 times 2. And the particle's position will be 4 meters. And so on. Let's find the velocity of this particle. So if we take the derivative of our equation, that'll be f prime of x, we're simply going to get 2. So this tells us that the particle is moving at a constant velocity of 2 meters per second. This graph illustrates what we just did. The green line here represents the position of the particle with respect to time. Time is our x-axis. And the red line represents the velocity with respect to time. You can see the velocity is a constant 2 meters per second. And here it shows after 1 second, position is at 2 meters. At 2 seconds, the particle will be at 4 meters, and so on. Let's try this one. So let's say our equation to describe the position of a particle is f of x is equal to x cubed minus 2x squared minus 2x plus 5. That'll look like this on a graph, with x being in seconds. So if we take the derivative of this equation, that's going to give us our velocity. The derivative, f prime of x, is going to be 3x squared minus 4x minus 2. So we have our equation for velocity that's represented by the red line. I changed the color of the equation to correspond with the color of the new line. Now we're also able to take the derivative of our velocity equation. And if we do that, we'll have f double prime, signifying the second derivative, of x is equal to 6x minus 4. This is our acceleration. That'll look something like this on the graph. The purple line represents acceleration, our second derivative. We can actually take another derivative and get what's called the jerk. Taking the derivative again, that's going to give us our third derivative of x. That's going to leave us with just 6, which is just a constant. It's the pink line on the graph here. Now, what is jerk? Jerk is just a change in force. It can be felt as an increasing or decreasing force on the subject. Basically, it's a rapid change in acceleration. Look at it this way. Velocity doesn't switch on out of nowhere. It grows from a lower number to a higher number. So there must be some acceleration involved. Unless we're just looking at constant velocity. But in this case, we're not. We have an acceleration in this case. Also, acceleration doesn't just switch on out of nowhere. it grows from some low number to a high number. So there must be some jerk at play here. So in this case, we're looking at a particle with constant jerk. If we were able to take another derivative, which we could, but it would just be 0 since this is a constant, we would have a fourth derivative, otherwise known as snap. Our snap in this case is just 0. Basically, jerk is a rapid change in acceleration, and snap is just a rapid change in jerk. So we just went over a simple application of higher order derivatives in physics. We went over and visualized a couple examples. We also briefly talked on what jerk and snap are. We didn't go over them in depth, but we covered the basics. It's important that you're able to find these derivatives above anything else. I hope this was informative, and thanks for watching.